The Atwood machine. Two objects on the end of a string that pass over a pulley wheel. So we've looked at these already, perhaps by now. If not, that's fine too. I'm going to act as if we have not. Pulley's job is to change the direction of the tension force. A pulley is considered an ideal pulley if the following is true. Please stick this definition into your memory. An ideal pulley is massless, so the mass is very small compared to the objects on the rope that's connected to. So we can ignore the mass or the pulley. Also, the wheel has very low friction on the axle, so we can ignore friction at the pulley. If we cannot ignore mass or friction, then this turns into an entirely not different problem, it's the same situation, but we're going to have to use different strategies to solve it. Strategies we are not equipped for at this time. So, a lot of the times, not all, absolutely not all of the times, but a lot of the times we're going to use an ideal pulley, and that just means it's massless and it's frictionless. The tension throughout the rope is also going to be the same at any point on the rope. The idea of the pulley only changes direction of the rope. It doesn't add any extra tension to it. It doesn't do anything. The tension right here above this blue mass comes from the mass of the red block. I don't know if you can see this thing on my screen, but I'm trying to get rid of it. Come on! So that's how we're going to deal with it. So the mass of the red causes the tension over here, or the mass of the blue causes the tension on this part of the string. Pulley doesn't contribute at all. For right now, that's all we're going to deal with. If a pulley is not ideal, then the tension in the rope on one side is different from the tension on the other side. Again, later. Alright. So you can see in Atwood's machine in different way. You have where you have two masses hanging over a pulley. You could have a whole system of pulleys. And the idea of a pulley is it's a simple machine, right? So it makes it a lot easier for you to do work on these objects. And by do work, I mean transfer the energy. Transfer from no potential energy to higher potential energy. It's easier to do work, so you're having to you can exert a lesser force. Another Atwood's machine could look like this, where there's a pulley. Basically, if there's a rope and there's masses and there's a pulley involved, you're dealing with an Atwood machine, and this is how we're going to deal with them. The modified Atwood machine is the official name for this. And obviously the difference in these two is there's a surface here which may be frictionless, may not be frictionless, just depends on the problem. Alright, Atwood machine! Here we go. When the Atwood machine is released from rest, what is the acceleration? Oh, released from rest. What is the acceleration of the masses and the tension in the string? Assume the pulley is ideal. Let's start by agreeing that the heavier mass accelerates downward and the lighter mass accelerates upward. Now we draw free body diagrams, one for each object. Multiple objects, multiple free body diagrams. If we had 5 objects, if there was another mass hanging down here or another mass hanging down here, the more objects you have, then the more free body diagrams you'll need, unless you're just looking at the entire system, in which case you would only need one. It's probably not going to be the case. Same string, same tension, because it's an ideal pulley. Get out of the way. For the first one, we have, well, I know it's the first one because it's capital M, so it's a bigger M, right? And then the second one would be the smaller m. Relatively the same free body diagrams, right? Tension going up, weight going down. But notice what's different and what's the same. We have a really small arrow going down for the weight of the red object, And then we have this tension going up, which is much greater. So just by looking at these free body diagrams, I know that the right is going to go up and the left is going to go down. Notice the length of this tension arrow. It is exactly the same because we're dealing with an ideal pulley, so the tension is the same all the way throughout the string. The pulley just changes the direction, right? Each free body diagram is then going to become a Newton's second law equation. Stuff that makes it go minus stuff that holds it back equals mass times acceleration. Stuff that makes it go minus stuff that holds it back equals mass times acceleration. Now, if we write those two equations in a certain way, it's going to make our lives easier. That certain way is stack them on top of each other. If you've ever worked with systems of equations in math class, that's what we're doing right here. If you have not worked with systems of equations in math class, it's okay. This is how we deal with an Atwood machine problem. All right, so we have big mg. Maybe you use m1, subscripts, doesn't matter. Whatever you want to call it, as long as you can differentiate between the two different masses, because they're two different things. Mg, stuff that makes it go, minus stuff that holding it back, stuff holding it back equals ma. All right, so now we have two unknowns in each equation. We don't know what the tension is, we don't know what the acceleration is. We don't know what the tension is, we don't know what the acceleration is. So let's eliminate tension by adding all four terms on the left and setting it equal to both terms on the right. You can see tension is positive here, tension is negative there, so tension is going to go away. And what we're left with is big M times G minus little m times G. Let me get my pen. So the tension is positive here, tension is negative there, so that goes away, and what we're left with is big mg, so this one, minus, this is a negative smaller weight, right, minus the smaller weight equals this plus this. Big M plus little m times a. This is just rewritten in a way because it's combined. The acceleration is the same for each term, but you can write it like this. It's just more terms means more ability for error. So, and we're solving for a, so you kind of want it to clean it up, right? Pull out the a because a is the same for each of these, and you get here. I might have just gone a little bit too far for a basic math thing. I'm sorry. So substituting in, you get acceleration equals 3 meters per second. And then you can take this 3 meters per second and go up here, plug it in here, or here, either one of these two equations, and just solve for tension. Because we would, if we have acceleration, then we can find tension. I would plug it into the second equation because tension's already positive. So I would add the weight of the small mass over here, mass times acceleration, just like that, and then solve for tension. But because I took so long, let me show you a shortcut in the next video.